Chapter 4. In Chapter 4, we begin our discussion of trigonometric functions. In the first section of Chapter 4, 4.1, we will recognize and use the vocabulary of angles. First, we'll describe what an angle is, use degree measures, use radian measures, convert between degrees and radians, draw angles in standard position, find coterminal angles, and find the length of a circular arc. 4.1, angles and radian measure. Let's first define what we mean by an angle. An angle is formed by two rays that have a common endpoint. All right, so let's say these two rays. All right, here's the common endpoint. We call that common endpoint the vertex. All right. If we start rotating, we generate angle theta. We begin on the side referred to as the initial side of the angle. And upon completing the rotation for angle theta, we have what is called the terminal side of angle theta. All right, so that's an angle. Now we can also talk about an angle in standard position. An angle in standard position has its vertex at the origin. The initial side is along the positive x-axis. So we begin here, and let's say I rotate through it, starting with the initial side. Here's the terminal side. Let's call this angle alpha. So alpha is considered to have been drawn in standard position. Alpha is positive. To generate positive angles, we move in the counterclockwise direction. All right? Another angle drawn in standard position. Let's consider the angle. Again, the vertex has to be at the origin. We begin the initial side along the positive x-axis. So let's start. All right, so let's say this is my angle. This is the terminal side, and let me call this angle beta. All right, beta is drawn in standard position. Beta is also negative. To generate a negative angle, we move in the clockwise direction. Okay, one way to measure angles is in degrees. So let's consider we had a circle, and if we make a complete rotation out this circle, so if I start here and make a complete rotation, we know that we've completed a rotation of 360 degrees. All right? Let's say that 1/4 of a complete rotation would put me where? 1/4 would put me here. All right, so if I go here, I have what is called a right angle. This is 90 degrees. All right, and this is a right angle. All right, as you know, right angles measure 90 degrees. So this is 1/4 of a complete rotation. All right, let's introduce some more terminology here. Let's consider an angle. All right, and let's say it's here. And this is my theta. All right, this is called an obtuse angle. All right, an obtuse angle, theta, is measures between 90 degrees and 180 degrees. On the other hand, let's say we have this situation, and let's call this theta. All right, this angle, theta, which measures between 0 degrees and 90 degrees, is called an acute angle. Let's do one more. All right, let's take 1/2 of a rotation. All right, so if I start here, take half, it's going to put me here, and now theta is 180 degrees. All right, so, and we call this a straight angle, which measures 180 degrees.
That's fine.
All right, using radians to measure an angle. All right, first of all, let's define what we mean by a radian. So let's define what we mean by, say, 1 radian. All right, so let's consider the circle. All right, we use a circle of radius r. All right, so let's say our circle is of radius r. All right. Whose vertex is actually here, the center of the circle. Such an angle is called a central angle. Notice that this central angle, theta, intercepts an arc along the circle that has the same length as the radius of the circle. So that central arc there is r. So the measure of such an angle is considered to be 1 radian. So 1 radian is the measure of the central angle theta that intercepts an arc. Here's the arc, intercepting the arc. And the arc is of equal length as the radius of the circle. That's what we mean by 1 radian. Okay, radian measure. Before we look at the example, let's talk briefly about radian measure. All right, so let's consider an arc length S on a circle of radius r and the measure of the central angle theta that intercepts the arc, again, which is here, that intercepts the arc, all right, is given by theta is, let's say, this is the arc length, and this is where the central angle intercepts that arc. So to find the measure of theta, we have S divided by R, the radius of the circle, and of course this is in radians. All right, let's look at an example. A central angle theta in a circle of radius 12 feet intercepts an arc of length 42 feet. What is the radian measure of theta? All right, so again, we have what? We have our circle. All right. Has a radius of 12. Central angle theta, and it intercepts an arc of length 42 feet. So this is 42 feet. All right, this is also. So to find the central angle theta, by definition, we have S over R. In this case, S is 42. 42 feet. And R, the radius of the circle, is given to be 12 feet. All right, upon simplifying here, we get 3.5. So therefore, the radian measure of the central angle theta is 3.5. Okay, let's establish a relationship between degrees and radians. We compare the number of degrees and the number of radians, say, in one complete rotation. All right? So in one complete rotation, if I go all the way around, so this is one rotation, we know in degrees that this is 360 degrees is the amount of that rotation. So the radian measure of the central angle is going to be theta. All right, the arc length, if I make a complete rotation, S is going to be what? S is basically going to be the circumference of the circle. So I get S over R, where upon making a complete rotation, S is the circle's circumference, and R is the radius. So what do I have? What is the circumference of a circle? The circumference is what? 2 pi r divided by r. So what do we have? We have 2 pi. So therefore, the measure of the central angle theta is 2 pi. So what can we conclude? One complete rotation measures 360 degrees, and in radians, 2 pi radians. Therefore, we can conclude that 360 degrees is equivalent to 2 pi radians. All right? Or if I divide by 2, I get 180 degrees is equal to pi radians. All right, now let's convert from degrees to radians. To convert degrees to radians, we will be multiplying by pi radians over 180 degrees. And basically we're multiplying by what? That's a unit conversion factor. We're basically multiplying by 1 because pi radians is equal to 180 degrees. All right, so we have 60 degrees and we want to convert this degree measure to radians. So I have 60 degrees times pi radians over 180 degrees. Pi radians divided by 180 degrees. Basically, we want the degrees to cancel. What we have is 60 pi radians divided by 180. And if we simplify this, 60 into 60, 60 into 180, we get pi over 3 radians. So therefore, 60 degrees is pi over 3 radians. In the next example, we want to convert 270 degrees to radians. All right, so we have 270 degrees multiplied by pi radians divided by 180 degrees. So let's do this multiplication. The degrees cancel. So that's going to leave us with 270 pi divided by 180 radians. All right, and upon simplifying, we get what? 3 pi over 2 radians. In the next example, we will convert a negative 330 degrees to radians. So we have a negative 300 degrees. We're going to multiply by pi radians over 180 degrees. So what do we have? Upon simplifying, we have a negative 300 over 180 pi radians. We simplify this, we get a negative 5 pi over 3 radians. All right, in this example, we will convert an angle measurement from radians to degrees. And in order to do this, we will be multiplying by 180 degrees over pi radians. All right, so to convert radians to degrees, we're going to multiply by 180 degrees divided by pi radians. So in the first example, let's convert pi over 4 radians to degrees. So we have pi over 4 radians times 180 degrees over pi radians. Alright. The radians will cancel out this time. Alright, and what do we have? We have 180 degrees, and it's pi radians, so the pi. Okay. So we get 180 degrees over 4, which is, you do the division, 45 degrees. So pi over 4 radians is 45 degrees. In the next example, let's convert a negative 4 pi over 3 radians to degrees. We do this by multiplying by 180 degrees divided by pi radians. So what do we have here? We have a negative 4 pi over 3 radians times 180 degrees divided by pi radians. Alright, if we simplify this, the radians, pi, so we're left with 4 times 180 degrees divided by 3. Alright, negative. Alright, so what you get is, if you do this, you're going to get a negative 240 degrees. In the next example, let's convert 6 radians to degrees. Alright, so what do we have? We have 6 radians times 180 degrees divided by pi radians. Alright, when we simplify this, we got 6 times 180 degrees divided by pi. Alright, if you do the multiplication and the division, 6 times 180 divided by 3.14, you're going to get 343.8 degrees. Alright, let's see what it means to draw an angle in standard position. Alright, to draw an angle in standard position, there are some requirements. The first one is that the vertex is at the origin. So we're going to start, the vertex of the angle is going to be at the origin. And the initial side of the angle lies along the positive x-axis. Alright, so let's express 3 pi over 2 in standard position. Alright, so 3 pi over 2, alright, that's actually 3/4 of a revolution. So 3/4 of 2 pi is actually 3 pi over 2 radians. Alright, so if I go 3/4 of a complete revolution, so I'm going to start here, you start along the positive x-axis, alright, and we're going to go all the way, alright, so this becomes 3 pi over 2. And this is the angle in standard position, what we call drawing the angle in standard position. The initial side of the angle is along the positive x-axis, and the vertex is at the origin. All right. Let's look at another example. All right. Let's look at pi. Let's say theta is pi radians. All right, what would it mean to draw this angle in standard position? Well, actually, this is what? Pi radians would be a half of a revolution. All right, so half of 2 pi is pi. So in standard position, all right, I know that the vertex is going to be at the origin, and I'm going to begin along the positive x-axis. So pi radians would be beginning here and here. So this would be pi. All right, pi radians. All right, expressed in standard position. All right, let's try another one. Let's take the angle theta to be pi over 4. All right, so an angle that measures pi over 4 radians, all right, it's a positive angle, all right, and pi over 4, all right, is actually an angle generated 1/8 of a revolution. So that's 1/8 of 2 pi, which is pi over 4. All right, so in standard position, all right, so 1/8 pi over 4 would be, all right, roughly here. So here is theta, and this is pi over 4, with the initial side along the positive x-axis. All right, just more examples of drawing angles in standard position. So let's take the angle theta to be a negative pi over 4. All right, to draw this angle in standard position, all right, and it's a negative, so negative angles are generated clockwise. So a negative pi over 4, so we begin with the positive x-axis, all right, and we rotate 1/8, so it's roughly here. So this is a negative pi over 4. All right. Let's take another one. Let's take the angle alpha. It's 3 pi over 4. To draw this angle in standard position, all right, beginning along the positive x-axis. So we have, you can kind of, this is, all right, this was pi over 4, 2 pi over 4, 3 pi over 4. So actually it's here, and this is the terminal side of the angle. All right, so this is 3 pi over 4 in standard position, and the vertex is at the origin. Let's do one more. Let's take the angle beta is equal to a negative 7 pi over 4. All right, so let's see, in standard position, all right, it's a negative, so we want to generate the angle theta in the clockwise direction. All right, so we have, so beginning here, we have, like this. All right, so we begin here. This is a negative pi over 4, a negative 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi, 6 pi over 4, and this is the terminal side of 7 pi over 4. So this is theta is a negative 7 pi over 4. Okay? All right, let's discuss what we mean by coterminal angles. Two angles are coterminal that have the same initial and terminal size, but possibly different rotations. In this case, we call the two angles coterminal. How do we find the coterminal angles? How do we find an angle that is coterminal to a given angle? All right? By increasing or decreasing the degree measure of an angle, first if we draw the angle in standard position and we either increase or decrease that angle measurement by a multiple of 360 degrees would result in an angle that we say is coterminal. So if you're given an angle theta, let's say we're given an angle theta, all right, and to get the coterminal angle for theta, we're either going to add or subtract multiples of 360 degrees, all right, where k is an integer. All right? So let's look at an example. So let's find a positive angle less than 360 degrees that is coterminal with a 400 degree angle. All right, so let's find an angle that is coterminal with the given angle. All right, and we want the coterminal angle to be less than 360 degrees. All right, so to get the coterminal angle, we have 400 degrees minus 360 degrees. So we're going to get what? An angle of 40 degrees. So therefore, an angle that measures 40 degrees is coterminal with a 400 degree angle. All right? Let's do another example. All right, let's find an angle that is coterminal with an angle that measures a negative 135 degrees. All right, so we have an angle that measures a negative 135 degrees. All right, so we want to find a coterminal angle, and we want that coterminal angle to be less, we want it to be positive and less than 360 degrees. So to find that, we have a negative 135 degrees, and in this case, we want a positive angle, so we're going to add 360 degrees. All right, and if we do the math, we get 225 degrees. So an angle that measures 225 degrees is considered to be coterminal with an angle that measures 135 degrees. Okay, let's find a positive angle less than 2 pi that is coterminal with the given angle. All right? So we have an angle that measures 13 pi over 5. All right? So we're going to either increase or decrease the radian measure by a multiple of 2 pi. All right, so we obtain the coterminal angle, in this case, by subtracting. So we have 13 pi over 5 minus 2 pi. All right, and let's see what this is. So we have 13 pi divided by 5 minus 2 pi, but 2 pi can be expressed as 10 pi over 5. So that now we can simplify. 13 pi minus 10 pi over 5 is 3 pi over 5. So an angle that measures 3 pi over 5 is coterminal with an angle that measures 13 pi over 5. In the next example, again, we want to find a positive angle less than 2 pi that is coterminal with the given angle, a negative pi over 15. All right, so in this case, I want a positive angle. It says find a positive angle less than 2 pi. So in this case, I need to add 2 pi. So I have a negative pi over 15 plus 2 pi. All right? So a negative pi over 15 plus 2 pi is a negative pi over 15, and 2 pi is equivalent to 30 pi over 15. 15 into 30 is 2, so we get 2 pi. So now adding, I have a minus 11 pi, minus pi over 15 plus 30 pi over 15. What are we getting? We're getting a positive 29 pi over 15. So therefore, an angle that measures 29 pi over 15 is coterminal with the angle that measures a negative pi over 15. To find a positive coterminal angle less than 360 degrees or 2 pi, it is sometimes necessary to add or subtract more than one multiple of 360 degrees or more than one multiple of 2 pi in order to obtain a positive angle less than 360 degrees. All right, let's look at an example. Find a positive angle less than 360 degrees or 2 pi that is coterminal with an angle that measures 855 degrees. So we want to obtain a positive angle. So for an angle that measures 855 degrees, it will be necessary to subtract 2 multiples of 360 degrees. So I have 855 degrees minus, all right, and I want 2 multiples. So that's times 2. So what do we get? We get 855 degrees minus 720 degrees. And when we subtract, we get the positive angle 135 degrees, which is less than 360. So therefore, an angle that measures 135 degrees is coterminal with an angle of 855 degrees. All right, let's discuss what we mean by the length of a circular arc. All right, so let's see. We can use the Radian Measure formula. We said that the central angle was S over R to find the length of an arc of a circle. So if we have, all right, so here's the radius. And here's my arc, S, and here is my angle theta. So remember, S represents the length of the arc intercepted by the central angle theta. All right? So in this case, we need to now solve for S, the arc length. But in this formula, if we have theta is S over R, so that tells us that S, the arc length, is going to be R times theta. All right, let's look at an example. A circle has a radius of 6 inches. Find the length of the arc intercepted by a central angle of 45 degrees. All right, so how do we begin this? So the formula, S is equal to R times theta, can only be used when theta is expressed in radians. All right, and our theta center angle is given in degrees. So the first thing we need to do is to convert 45 degrees to radians. And we do this by, remember, 45 degrees times, we multiply by pi radians divided by 180 degrees. And this gives us 45 divided by 180 pi radians. Upon simplifying, we get pi over 4 radians. So 45 degrees is pi over 4 radians. All right, now we can use the formula S, the arc length, is R times theta. So in our problem, what do we have? Let's see what's given. We see that the radius R is 6 inches. So R is 6. The measure of the central angle in radians is pi over 4. So theta is pi over 4. So the length of the arc intercepted by this central angle is, using our formula, S is equal to R times theta. So we have R is 6 inches, times pi over 4. Theta is in pi over 4. So what do we get? We get 6 pi over 4 is going to be, if I simplify that, I guess 3 pi over 2. All right? And of course, this is in inches. All right? And 3 pi over 2 inches, if we use our calculator, we obtain 4.71 inches. All right, so the arc length S is 4.71 inches. All right, the last idea here is that of linear and angular speed. So if a point is in motion on a circle of radius r through an angle of theta radians in a particular time t, then the linear speed is given by v is equal to s divided by t, where s, of course, is the arc length. And given by, we recall that S is just r times theta. The angular speed is given by omega is theta divided by t.